In this video, we're going to continue talking about the bell curve or the normal distribution curve and a little bit of statistics, just basic statistics to get us started in understanding error analysis and understanding errors in surveying and how to deal with them and what they mean. So again, we said that almost all surveying measurements follow a normal distribution curve. That means that if we have our true value here, our measurements are going to fall on either this side, as in being like, well, it was really, let's say that my measurement was 1. Well, this right here, this area is 1.01, 1.02, 1.03, maybe all the way out to 1.1, right? And usually with random errors, you have equal sides here where you could also be missing the mark by 0.01, 0.02, all the way to 0.1. And this is kind of, this side's a mirror image of that side, or very close to. And we talked about a histogram where we plot those, the frequency at which we take different measurements, because we would have to repeat a measurement many times to be more certain that we are actually getting close to its true value. And if we have an infinite number of measurements, we are going to see that they follow this pattern. Now, this is very studied in statistics. You may not have ever taken a statistics course, and if that's the case, that is fine. I'm going to explain just enough so that you understand its application to this particular course. So if you see this curve, we have 2 points here called PI. PI stands for point of inflection. So let me write that down. Point of inflection. The point of inflection is the point at which our curve changes from convex to concave, or vice versa, depending on how you look at it. But at this point, the slope changes, right? Well, it's changing throughout, but it changes from this to that. So at this point, so you're going to plot your bell curve. This point, you're going to mark it down, and that's going to be your standard deviation. So standard deviation is also the point at which there's, if I check the area under the curve is 68.3% of the area. And once you figure out what this number is, you can also figure out what the 2 standard deviations, 3 standard deviations, pretty much whatever distance between here and the mean is. If you make the same distance continuing to the left or to the right, then if this is 1 deviation, that's 2 deviations, this is 3 deviations. And the area of the curve changes. Now, we could estimate the area of the curve ourselves, but we're just going to use a table that is given to us so that we don't spend the time doing that kind of stuff, because it's not necessary for this class. But the point is, you can calculate that point, and you can calculate your standard deviation with a formula. So let me get to that. So again, what does this mean? The point of inflection is where the slope of the curve changes from concave to convex, or vice versa. The residuals at the PI are called standard deviations, and this value indicates the reliability of repeated measurements. It's telling you, remember we were talking about the distance. If we had this graph and we have all these points, it's a way to kind of calculate a number that represents how off are we from the mean. Not, and I'm going to talk about, there's a difference between standard deviations and mean error, standard mean error. And what it means is, here we're looking at the reliability of individual measurements in general. So the formula for this is, this is sigma is equal to plus minus the square root of the summation of the squares of the residuals over n minus 1. Now, I want to clarify that v square is the sum of the squares. Is you square first and then add. So, and this should be obvious from the notation, but in case it isn't, this is really this. Let me give myself some room here. Oops. Oh, come on. Okay. So this is equal to plus minus the square root of, this is going to be x bar, meaning my mean, minus x sub 1, the first measurement that I did, squared, plus x bar minus my second measurement squared, plus, you're going to keep doing it all the way up till x sub n, and then you're going to divide that by n minus 1. That's what that means. So we're actually going to do an example. You can calculate the standard deviation, and then we're going to use the standard deviation to find the probable error. Okay, so here let's continue with this. The probability of error at various positions on the curve can be determined by a formula that looks the following. It's E sub p is equal to C sub p times times sigma, where E is the error, and C, this is going to be a constant number based on a particular probability we're looking at. That's what P comes from, a particular probability. So I can find out what my error is when I only care to have 50%, like a probable error of 50%. So we have, and this is going to make more sense here when we see an example, but let's say that I want to know, so probabilities for certain error ranges, this is going to help me find an error range. And so whenever you have let's say that you made some sort of measurement, and it's 1.23, right? So it could be 1.23 plus minus a certain number, and you're going to say there's a 90% probability that this is accurate. So if you want a 90% probability that this number you came up with, let's say 1.23 plus minus 0.52, then you're going to look at, so if you want a 90% probability, you're going to multiply your standard deviation times this constant, okay? And right now you don't have to quite understand where this constant came from. All we need to know is that you're going to use it to calculate the probable error. So you can know your range with as much accuracy as you want. It can be as low as, 38.3% or as high as 99.9%. If you want very, very good accuracy, how big is your range going to be? So as your probability gets smaller, and I'm going to write this, where do I write this? Let's see. As your probability gets smaller, your range gets larger. So there's only a 50% probability that my error is between 1.23 and plus minus 0.01, for example. That's 50%. I'm not making these numbers up, so it's just to illustrate an example. But if I want to know with 99.9% certainty, my mean's the same, but what this number is going to end up being is like plus minus 0.95 or something, right? So obviously you're very certain that this value is going to be within this range, because this includes numbers as high as 2.18 and as small as I don't want to do math in my head, but anyway, you see what I'm saying? So this is telling me I have a small range, but I only have a 50% chance of actually having a measurement within this range. Or if I want to be very certain, my range is going to be quite large. All right, so let's do an example. So this is the same equation, only remember that this is the equation for sigma, so it's just a kind of fully written out one. Oops. When a single quantity is measured several times, the probable error of any one of the measurements can be determined with that formula. Let's do an example. We're going to find the 90% error for the following distance measurements. So let's say that you went out and you measured something and you came up, you did it 10 times, the same measurement 10 times, and you came up with these numbers right here. So how do I know the 90% error? Well, the first thing I have to do is, so step one, I'm going to find the mean or the average, right? Remember that to find average, you add up all the numbers and then you divide by the number of numbers, in this case 10. And in this particular example, my mean is 130.17. 2. You're going to find the standard deviation. Standard deviation. So the way you calculate this is the following. So sigma is equal to plus minus the square root of, let's see, 130.17 minus 129.40 squared plus 130.17 minus 132.1 squared plus, you see what I'm doing now, right? So if you do that, you're going to have 10 of these added together, then divided by n minus 1, which is 10 minus 1 equal 9. And then whatever number you get, you're going to get the square root of that. And finally, we are going to have, so the error at 90% is equal to C 90% times, let's see, the square root of 15.014 over 9. That's as far as I have gotten with this part. And let's find out what C90 is. So we'll have to go back to that table. At 90, we said we're going to multiply our standard deviation times 1.6449. So I have to go back. So this is now E90 is equal to 1.6449 times this number, whatever that number is. I'm going to do it all in one step in my calculator. And this gives me an error or a range of plus minus 2.13. That means that my measurement is 130.17 plus minus 2.13, and I'm really only 90% sure that any individual measurement will fall in this range, and this range covers, let's see, 132.30 to, sorry, I should have done it like this, to, let's see, 130.17, this is going to be 128.04, right? Did I did that right? So my measurement is going to fall in this range, and I'm 90% sure of that. Now, remember, if this number gets larger, let's say that we do it with 99.9, this number, as my probability gets higher, this number is going to also, oops, keep clicking on things by accident. So as the probability, actually as the probability gets larger, I wrote this down. I was thinking as the probability gets smaller, as in like there's a smaller thing left. Sorry about that, that must have been confusing. So as the probability gets larger, so does the range. So in this situation, if I wanted to know with 99.9%, this would surely be 4 point something, and my range would be larger. If I wanted to know 50%, then this is going to be a smaller number, but you'll only be 50% close.